will be given by Dr. Eric Hall. So Eric is a Baxter Fellow and lecturer in applied mathematics at the University of Dundee, and today he will talk about graph-informed neural networks for multiscale physics. So please go ahead, Eli.
Hi, thanks for coming, especially after the snorkeling. You're probably falling asleep. Do some star jumps if you are. Right, so it's very nice to be here in person with very nice people, and I've really enjoyed the conference so far. So what I'm going to tell you about today is a project that involves some predictive stochastic modeling of systems that are of interest in energy storage applications. It's maybe not as heavy. I knew I was going to give a talk on the last sort of time slot, so maybe not as heavy and as interesting as Luis's talk, or as complicated. So this is some joint work with Soren Taverniers, who is at Stanford, and now he's at Park. Marcus Katsoulakis, who some of you probably know, he's at UMass Amherst, and Daniel Tartakovsky, who's at Stanford. In energy resources engineering. And so some of the papers that this work is involved in are these ones in JCP. Right. So what am I going to do today, right? So the general plans to start by giving you some overview of our approach, right, to generating some statistical surrogates for complicated systems and involve multiscale and multiphysics interactions, to tell you about sort of the motivation, the strategy that we're thinking about, right? And as I said, right, we're going to look at two different examples, hopefully, unless I'm severely needing to accelerate, then we look at one example. But you know, if you have any questions, you can feel free to stop me. Okay. After I give you some overview, right, the two examples of this supercapacitor dynamics, and then a Langmuir adsorption model that comes up in hydrogen fuel cells, and then sort of tell you a little bit about, you know, using these surrogate models, surrogate models, and in particular some tools using mutual information for doing some sensitivity analysis that fits within this graph-informed neural network framework. I apologize to the hosts for the bad puns. So here we start then, gin-based decision making. So what's sort of the context here? So, I mean, simulations, right, are playing a vital role in many domains of science and engineering to aid decision making, right? And, you know, when we have these complex multi-scale systems, right, where you have, you know, multiple scales, hopefully you can see the arrow here in length and time, it becomes complicated, right, to characterize all the uncertainty and error that enter at different stages of the workflow. And, you know, we're really interested for these sorts of systems of accelerating engineering design, right? So when we have the supercapacitors, when we have the fuel cells, it's not like these are super high consequence decisions, but nevertheless, if you can shave a few years, I mean, how do they make these supercapacitors and things? Give some poor material science student a PhD project, and then 5 years later, they make some suggestions. And if you can shave a few years off of that by doing some, you know, computational science and engineering, well, you know, we've made our value in the world clear, right? And in particular for these sorts of you know, multi-scale models, right? It's very complicated to be able to sort of do these UQ tasks that involve you know, multi-query objectives, right? So you need to not only to do UQ in these sorts of situations, run a system once, but many times in order to say anything, right? So what are we going to think, right? So here, right, we have these multi-scale models, and typically we think about, capturing the uncertainty in these physics-based models by, casting some deterministic model into a probabilistic framework. So here, what I mean is we're going to think about the control variables, right, as being some random inputs to the system, with distributions that are derived from some available domain knowledge. And that includes, as well as actual data, engineering design constraints, things that are known by the engineers that are designing the systems. And what we're interested in is sampling output quantities of interest, right? Typically by simulating the physics-based models. If we're doing this and we have these UQ and sensitivity analysis questions that we'd like very much to do if we want to do simulation-aided design, what can we do to accelerate things? Statistical surrogates that emulate some system response are used very widely, right, to enable some faster generation of data to speed up these multi-query tasks. And I mean, the many options, right? I mean, we heard earlier kriging, one of many, right? One important thing to remember is, right, that when you have these statistical surrogate models, they're not an attempt to capture a simplified representation, right? It's not a reduced order model in the sense that you're trying to capture some simplified representation of the dynamics of some system. Is that a question, Christian, or just a scratch at the nose?
Yeah, I think I understand.
Okay, so I mean, a statistical model, statistical surrogate, as opposed to something where we're trying to capture, I mean, so you can imagine like some coarse graining model, right, where you're lumping together dynamics. This is a type of reduced order model where you're trying to still capture some simplified representation of the dynamics of the system. If it's just a statistical model, yeah, okay, it's you're not actually technically trying to represent the system and capture its features that way, right? And I think for a lot of these engineering design applications, we're just trying to accelerate things. Again, it's not a high consequence decision, so this is a place where statistical models are sort of appropriate. So, what's here, scientific machine learning is another way of getting a statistical surrogate model. And I mean, I think everyone here knows, right? I mean, it's dead easy, in particular because of all these off-the-shelf software products. It's not hard. What is hard is thinking about sort of the challenges that are involved. I mean, because these are written by computer scientists, right? And I think, simulation, any sort of scientific machine learning requires a little bit of sophistication. Yeah, I mean, I don't want to make it seem like this sort of image classification problem is trivial. I just love the idea of your chihuahuas and blueberry muffins. Stare at the chihuahuas for a few minutes and try and decide whether they're blueberries or eyes and noses. But I mean, so something that's, I think, very different here with this scientific machine learning, in particular when we have models, is that we need to try very careful to incorporate the models into our, into our modeling paradigms. Right, because here the situation is different in terms that we're driving the data generation project. And is that a question?
Yeah.
Cheheb?
So you are trying to
for the people, I have the microphone so the people online can hear me.
Yeah.
So you can do the same thing.
So when you are telling that you incorporate models, does it assume that you can incorporate stochastic and deterministic models also? Because if you have different scales, I mean, that you deal with.
Yeah, so you'll see a little bit more details later. So I mean, none of the models we're going to look at, we put the distribution on everything. And I think that's useful for a lot of reasons, because you could also want to measure, like, you know, errors and discrepancies in terms of some range of values, right? Some distribution. So even if you have something that's deterministic, you know, just put a delta function and
Okay.
live with it. Right. So another thing is that when we have our, you know, our sort of physics-based models, right, it's often the case that, you know, the data is sparse, right? I mean, if there was lots of data, then we wouldn't probably need a model to help make predictions in the first place, I guess, yeah. So one of the things that we've been thinking a lot about with Marcus and Daniel is, right, how to incorporate this domain knowledge into our sort of machine learning workflows. Yeah. And of course, you know, when you do have these models, right? I mean, the machine learning models, right? Probabilistic models, right? These are essentially black boxes. So, you know, you need to think of clever ways of interrogating these black boxes. And with the graph-informed neural network approach I'll show you, it also suggests using certain tools to sort of do that interrogation, right? So, you know, the outputs from the neural networks are non-identifiable and they lack, you know, interpretability, right? You can't identify cause and effect in the models, and they lack explainability, right? So, you know, you have to do some interesting shuffling to be able to, you know, put the outputs in the context of the processes and the data that was used to generate the model. So, okay, what am I trying to tell you about today, right? How should we think the domain knowledge be incorporated into some supervised machine learning, right? And how should we be, you know, representing this domain knowledge and modeled? So our GINs here, our graph-informed neural networks, right? The idea is to endow our statistical surrogate models with some hierarchical structure, right? So, you know, deep neural networks learn correlations, right, between things that are essentially flat, right? I mean, they do a really bad job of representing and capturing hierarchical information in the data. So the simple-minded thing that we propose to do is to add some hierarchical structure to such models. So on some other level, right, you know, the graph-informed neural network approach that I'm telling you about incorporates these sorts of very traditional methods in statistics, right, probabilistic graphical modeling, with this machine learning workflow, right? And one thing I'll say, and, you know, if anyone has some interesting models here that they know about, but afterwards they say, this is sort of interesting. I think, you know, this idea of using the probabilistic graphical modeling to represent the system is something that resonates really well with domain scientists and engineers. So what I mean is it's sort of a more intuitive way of discussing models with them that I think is not a bad way to help facilitate some, you know, interdisciplinary collaboration. Right, with these graph-informed neural networks, as I said, right, the idea is that we want to endow our deep neural networks with some hierarchical structure, right, to deliver a domain-aware surrogate. And in particular, in the systems that I'll show you, right, we had these multi-scale interactions where we had computational bottlenecks. So the sort of the graphical structure is helping to guide both the learning and the prediction, right? So you have, you know, you notice here the control variables still keep their structure, right? So it's not like we're thinking always about having a flat input, right, to the neural network, right? You want to keep and maintain structure. And you don't want to learn everything, right? You only want to learn the things that are a problem, right? Like here, the sort of the deterministic commoditization, right? The upscaling of the system from microscale to macroscale. And you also want to retain sort of the graphical model, probabilistic graphical model, to aid in explainability of the outputs, and to be able to interrogate the model using, for example, mutual information. Of course, yeah, I thought I just mentioned, we've already seen like, physics informed neural networks, and there are also other ways of incorporating physics, right, which is a type of domain knowledge into systems. Sort of the very simple-minded thing we did was not to use as well a physics-informed neural network, but I mean, there's nothing stopping you from sticking here with this neural network surrogate model, something more muscular, like a physics-informed neural network, or a structure-preserving neural network. For example, like the ones that Nate Trask at Sandia is thinking about for high consequence decisions, right? So this graph-informed neural network approach, right, is non-intrusive, and the idea is not telling you, you have to stick with this particular neural network architecture. Nevertheless, for sort of the multi-scale systems that we're looking at, I mean, it's also not entirely clear how you enforce all those things in the loss function. Some of the steps in this graphical model for the supercapacitor involve, some optimization problems. Right. And then, of course, I tell you at the end about doing some mutual information sensitivity analysis, because really what started the conversation with Daniel and Soren was they had a problem, and they wanted to be able to sort of say, tell me which control variables in the system I should modify to get a targeted response. Yeah. And that, it's the sensitivity analysis, the global sensitivity analysis type stuff. And when you have this statistical model, oops, it's got a tiny scroller on this key mouse that changed. Right, just using the physics-based model, they weren't really able to get a sort of identifiable ranking, for example, of which parameters they should be looking at. And in fact, first they had used Sobol indices and got crazy things because there's a large space of correlated input variables, and Sobolev indices are not so useful then. Okay, so that sort of was the summary, the overview, and now I tell you about two models in particular. Okay, any questions so far? No? Okay. Right, so here we're going to build a graph-informed neural network for some supercapacitor dynamics. So what is this thing? Okay, a supercapacitor, I mean, as it sounds, super. Right? You want to build a capacitor that has some properties that are not typical, right? And so you need to design the materials to go into the capacitor to try and do that. But what you can control at the microscale, right, are things like the material that you're designing. But what you want to have, right, is an objective at the macro scale, right? So you want it to have some particular conductivity properties, something like this. Okay, and what these capacitors look like, right? Well, they're typically carbon-based hierarchical nanoporous materials. Okay, here on this slide is a picture of just like one example, okay, of a cell, right, from the nanoporous material. So you're thinking in, if you're looking down at it, right, you have like some nanopores here, these gray sort of inclusions, or some solid structure that get laid down, and this is like one little piece, right, of a million by million by sort of million type thing, right? And you have some electrolyte, right, that's here in this pore space, right, the empty space, and there's a diffusion of these ions, and the state model for the electrical double layer capacitor is parameterized by some effective constants at the macro scale. And the question is sort of, okay, how can we try and engineer the system, right, to have perhaps particular effective rate constants. Okay, so what does sort of some of the equations look like here? So already you see that this is just a particular geometry that can be much more complicated. They sometimes try and put them in a more interesting way, these sorts of occlusions. And sort of the capacitance properties of the material have something to do with the formation of an electrical double layer on the interface between the solid structure and the pore space, right? So it's how it's being a capacitor. Okay. So these effective ion diffusion parameters, for example, the diffusion of cations and anions, the electrical conductivity, and the transference number, these are sort of things that we think of as being our quantities of interest in this example. How do you get these macroscopic variables, right, from the microscale system? Well, you could imagine, you might say, okay, we just track the diffusion of the ions throughout this big material. But, okay, so that's at the microscale, that's sort of impossible to do, right? So you need to do some sort of upscaling, okay? You have multiple choices for how to do such upscaling. What's typically used in engineering is they use some phenomenological properties. Right? So they do some phenomenological relations between the microscale and the macroscale model, which is cheap to compute with, but not very accurate. Yeah. And moreover, if we're thinking about, okay, we put some distributions on our microscale variables. Yeah, if we only have a phenomenological model, it's not really a systematic way of propagating distributions on the microscale to the macroscale. So the way that we get these macroscale quantities is through some deterministic commoditization, right? So this involves solving some closure system to go from microscale quantities to macroscale quantities. And again, this is sort of, like I said, you can't make the predictions just by tracking things at the microscale. So this macroscale continuum equations for these quantities are sort of your best case scenario for making computations, but they're still very expensive to compute with, as we'll see. Okay, yeah, so this is just the upscaling by homogenization. I won't bore you with equations at almost 6 o'clock in the evening. I just summarized them, right? So we have some quantities of interest at the macroscopic scale, right, which are related to diffusion quantities, parameterize the models that are characterizing the behavior of our electrical double layer capacitor cells. And we have a range of input variables, right, that all have something to do typically with microscale quantities or operating quantities. And in particular, there are two things which are sort of the expenses bit here, right? And that's the upscaling by homogenization, right? So solving the closure equations, as well as some optimization problem for finding the EDL, the electrical double layer, in the system. And as I said, right, we want to think about the variables, our control variables, as being something that we'd like to tune, right, at the microscale to try and achieve some macroscopic performance criterion, some goal, some target. But again, right, these quantities, right, the macroscopic diffusion quantities, I said, right, they're this is not the end of the story, right? They form their state variables for some electrical double layer capacitor system. So so the starting point then is to think, okay, well, really what we're interested in is a very big joint distribution, okay, for all the variables in our system. And right, with that, we might say this is horrible. You want to think about some very large joint distribution, but again, this is where we want to incorporate the domain knowledge, right? So it's not like all the variables here are independent of each other, right? They're very much dependent on each other. And the idea is to break down this large joint distribution into products of smaller parts, right, that are easier to compute. So the idea here is, you write down a probabilistic graphical model for the joint distribution, right? Just a way of decomposing some large complicated joint distribution into a product of conditional distributions and marginals. These can also be represented by sort of directed acyclic graphs. So what is in sort of a Bayesian network? This directed acyclic graph, probably people are also familiar with Markov random fields, right? These are not directed. Yeah. I think for a lot of the sort of engineering design problems where you don't have any sort of communication, this idea of directedness is a bit clearer. Yeah. Right, we have our control variables and we put some distributions on them. To be honest, it's similar to what Professor Knio said in his talk. He said, I don't know if anyone paid attention, but he made a comment about how, the ranges of the variables were sort of the things that were important and not the shape, right? Well, we also sort of found the same thing. For the sort of the control variables, picking just, uniform distributions where we were very certain about the range was useful and easy to do. So what are these sorts of control variables? So some of them had to do with the geometry of the actual structure that's being built, right? And the way that these sorts of independences among the variables or the conditional relationships were selected was including information that Daniel and Soren had to hand about, for example, like this particular component in the system is engineered in Japan and they do beautiful work and it's very specific and it always meets their standards. But when we lay down these components, like the little circles, we're doing that here in the lab and that has way more variability in it. So that becomes suddenly the dependent variable. We also have things that are related to the EDL formation, like the Debye length and the concentration of ions in the electrolyte, right? So basically the makeup of the electrolyte, the sort of environmental conditions and operating conditions, so what sort of voltage you're putting on the thing. Right, you sort of, by keeping the structure, you're doing a similar thing to the physics and informal networks, and that you're pushing the system to sort of give some physically relevant predictions. So, right, this graph informal network is essentially some hybrid probabilistic graphical model neural network, where you're only replacing some of the computationally demanding nodes in the probabilistic graphical model with a deep neural network. And I think, yeah, this picture is a good one to show it, right? So, really, we want to be able to tune these control variables still, right? We keep the structured priors on the control variables to make sure that the output quantities are physically relevant. And yeah, you can still put whatever neural network you want there. If you really want to use some structure preserving sort of neural network, that's fine. So the actual training of the network, right, and the testing and the predicting, I mean, this is not anything that's advanced, right? We did nothing that was terribly ingenious in doing this. And in particular, we kind of didn't want to, because we wanted to see if we do something very simple, right, how much can you get out of it, right, for accelerating the design. So these things I will skip over because you guys know how to use TensorFlow, I'm sure. And the idea is that, you know, right, again, we need to predict joint densities and marginal densities of these quantities of interest, because these are forming, right, the state variables for some more complicated problem. And, you know, being able to predict what they are is useful. I guess one thing that I have these pictures here is not really to show you that you're able to make some prediction, but it's sort of important that okay, so we have this homogenized system, right, where we specify distributions on input variables. We do some deterministic upscaling. You get your output distributions. You use this to train a neural network. Why do you do this? Because you'd like to be able to use the neural network to make, for example, this kernel density estimates for output quantities. What can you see here? The output quantities, right? So here, for example, these joint densities of the diffusion and the transference number are very non-Gaussian things, right? They kind of look like bananas, maybe. Okay. So you know, the next question, right, that we wanted to think about was, how do you sort of do some sensitivity analysis for the system? And the graph structure sort of suggests certain tools. But first, I just show you one other system where here it's a nice example, because the actual structure is very simple. It's a very simple toy problem. And here you have a graph where the structure, right, is derived from data, right? So you might say, I'm not comfortable with the engineers and what they're saying about a system. Here's a simple example with just, you know, some data. So here, Langmuir absorption is a process where you have competitive dissociative absorption on a catalyst surface. So you imagine that you have some metal surface, and, for example, hydrogen and oxygen are adsorbing onto the surface, right? And you'd like to understand the coverage equilibrium. This is needed for example, hydrogen oxidation in fuel cells and batteries. Okay. Well, you can have a very simple physics-based model for the coverage dynamics of two species. Okay, here's just a system of ODEs, right? Where here the theta A and the theta B are some coverage dynamics. But what you'd like to understand is sort of the uncertainty in the coverage dynamics at equilibrium as functions of something called the absorption energies of each species, changes in absorption energies. And this is something that you can get data on using density functional theory. The reason I say it's sort of a toy example is because, well, you have here ODE, you can compute the steady state and know. So here we actually have a sort of a ground truth that you can look at for this simple example. So the equilibrium constants, right, in this ODE are given in terms of the changes in absorption energy by an Arrhenius law. And so, you know, for example, here you can compare, like, I mean, okay, you could compute for long times and look at the equilibrium coverages, right? Or you can get it by the Arrhenius law in this case, right? You say here you calculate with these guys, the Kas and the Kbs. And what's sort of interesting about the system is that you have data on, you know, for example, using different metals, right? And trying to see what their changes in their absorption energies are. So this picture at the left here, some, I mean, I say experimental data, but to you folks, it's experimental data. To people in chemistry, they say, ah, no, it's not an experiment. It's a numerical experiment, right? So it's based on a density functional theory, which is a molecular dynamics simulation. But this is sort of the way to calculate these things, and they're and so, okay, so what can you look and say about this data for the changes in the absorption energies? Well, these folks who are chemists said this is a nice linear relationship between these things. So that suggests a certain type of graphical structure in a probabilistic graphical model. Right, so the fact that you have this linear relationship, right, means that the conditioning, right, of EB given EA is looking like this, right? So here you build the probabilistic graphical model from data. And then one still has a question, okay, I mean, in this example, you know, the solution at equilibrium is known, wrote it down for you, but you could still pretend that there's a computational bottleneck and try to compute quantities of interest just to compare. Yes, and okay, I mean, yeah. So it can be done, and you know, again, here, if you really do want to compute some joint density, you need a lot of data points. Again, in this example, it's a toy example, so you can compute the equilibrium dynamics, but in principle, you know, might not have a solution like that and be able to do it, right? So here on the right, the sort of the gin-based surrogate predictions are very reasonable things. Certainly good enough to sort of help to design the system with. Yeah. Okay, so once you have this set up for describing the system, as I mentioned, it sort of suggests certain tools for interrogating the model, which again were the things that we were really after. So the last thing I tell you about today is some mutual information based global sensitivity analysis. And typically it's okay, this is maybe expensive to do, but if we have a surrogate model, yeah, run with it. Yeah. So global sensitivity analysis, right, is a tool, right, for peeking inside sort of black box models, and it gets used all over the place, right? So in traditional sort of engineering disciplines, right, you use variance-based methods like Sobol indices and total effects, and the idea is that you want to rank input parameters by how much they're contributing to the variance of some output parameters. But I would also say that they make some implicit assumptions about the model, right? So if you have large spaces of correlated variables, it's not so clear how to interpret Sobol indices and total effects. And as well, right, I showed you some funny banana-shaped distributions, which are not so Gaussian. So there's kind of a more fundamental question, like how much does the variance tell you about these non-Gaussian or worse, like multimodal distributions? So that's slightly of concern. It's not exactly like a completely model-free thing, right? Is what I'm saying. There's some implicit assumptions. So in sort of the statistical learning, right, you also use some things called shapely values and partial dependence plots and ICE. This is something about integrated conditional expectation plots for elucidating relationships between predicted responses and one or more features in a regression model. And again, these things are also, right, conditional expectation. I mean, they're depending on moments of the distribution. I think typically one doesn't use distributional based methods like mutual information because you need data to do this. But I think this is sort of where you know, having a statistical surrogate is the point, right? I mean, you can make the data. You don't have to worry. It's no worse, I think, than doing some, you know, bootstrapping, right? Okay. So what is the mutual sensitivity, right? Mutual information sensitivity index, right? So we're trying to judge the association between some input variable typically and some output variable. And I put this here, okay, a plug-in estimator. I'm not making a statement about the fact that this is the best way or the most efficient way of computing the mutual information, simply that it's an easy way to compute the mutual information, right? We generate some input data. We use our statistical surrogate to generate a corresponding response, and you can quite easily compute a plug-in estimator for example, the first order Mises. The other thing with the mutual information is that you know, you're able to also think about higher order effects by looking at conditional differential mutual informations. So you can sort of think about you know, our complicated systems here with correlated variables, and then this becomes a sensible thing to do. Right, I show you just, you know, you can compute. So for example, for this Langmuir model, right, you're able to compute some ground truth rankings using the physics-based model and the sort of different variations on using the GIN. So for example, getting it to sort of produce very much data versus not so much data. You get rankings that are fairly in agreement with it. What are the differences here? So the thing on the left-hand side are the actual Mises values, and on the right-hand side, it was using an algorithm for the ranking of them. For the supercapacitor dynamics, well, here we don't have like some ground truth, right? So we tried our best with the physics-based model, but the variability in the physics-based model, you can see, is not, I mean, you can't discriminate necessarily between the rankings, which is a little bit of a problem. But you know, we went back and computed based on the rankings with the physics-based model to see what the response was, and you can see that it's a sensible sort of thing. This mutual information as a sensitivity index, right? So you see an interesting response curve, which is this first thing on the left, right for you folks. First thing on the right. When the ranking is suggesting that the sensitivity index is that particular variable is telling you something interesting about the response, and you see a very flat, sort of uniformly uninteresting picture on the right, far right, for the least impactful ranked item. Okay. So then, right, what do you do, right? So the idea is that you would use these rankings to sort of explore sub-regions of the original parameter space in order to design experiments that you'd like to carry out, so numerical experiments with a physics-based model, or making more predictions with the surrogate model, and iterate, right? So, for example, trying to produce a response surface that has some effective conductivity, and using the GIN response surface, so the statistical surrogate response surface to identify parameter ranges that correspond to some targeted property, and to then generate some new rankings and to keep going until you find. And in that case, I mean, you've already trained the model, so you just get as much as you can out of it. It's not expensive to do this sort of thing with the surrogate. Right, so you know, the sort of simulation-based decision-making for complex systems, I think requires some more complex, applications of machine learning that, you know, try to incorporate domain knowledge about the system, particularly when we have our physics-based models and engineers. We don't want to throw away what they know. So we have this GIN surrogates that incorporate domain knowledge using structured priors, right, that are represented using probabilistic graphical models. We retain the structured priors on our control variables, and we sort of think about only bypassing sort of the computational bottlenecks in our physics-based model. And then we can use the statistical surrogates to do these sorts of you know, mutual information sensitivity methods, right, for determining, you know, and ranking which control variables are like most impacting, you know, quantities of interest. Yeah, so that's thank you for not falling asleep.
Thank you, Eric, for the talk. Let's see if we have questions. Yeah.
Many thanks, Eric, for the talk, for the nice talk. So in the first part, you did kind of propagation of the uncertainty from your input to your output variables.
Yes.
And why should I mean, okay, I'm not expecting this. Why should I believe that this method will be better than other methods like polynomial chaos or other things? What is the constraint for that? And my second question for the second part, did you also compare to other methods for global sensitivity like Sobol indices or so on to see?
Oh, yes.
Okay.
So well, I'll answer the first question second. So for the Sobol indices, like I said, and it wasn't for this. When you have large spaces of interacting variables, right, it's a real challenge to try and unpack how that should be interpreted, right? So there's nothing telling Daniel not to use Sobol indices, right, for his to try and say this variable is the one that's impacting the quantity of interest. But we have some other experiments where, you know, you're looking at like the transverse versus the longitudinal diffusion through a structured nanoporous material, and sort of the geometric variables which are controlling the opening through the transverse direction are the things that are decided to be most impactful for the longitudinal direction, which is not. I mean, it was a made-up system where we kind of knew that that wasn't the case. So I think the most complicated thing with the Sobol indices is trying to interpret them correctly when you know that, for example, I mean, because remember the geometry, right? Not all the variables sort of here that we had, like the porosity and the pore length openings and the size of the structure, the radius, right, for the structure. In terms of thinking about the stochastic homogenization, right, you fix a cell that's repeated. Sorry, the deterministic homogenization, you fix a cell that's repeated million by million, right, by some depth. And not all variables can be independent of each other, right? So it's a challenge there. And for this system, right, there was all sorts of other operating conditions, and that adds, right, not just the geometry, but all sorts of other interacting variables. So with the other question, right, should one use something? Well, here, right, it's not here, right? We have this homogenization. I try and go back to it for you, or I kill the computer. Oh, there we go. So here we have the closure equations, right? I mean, what should one do then? We would try and expand everything in a polynomial chaos expansion. I think here, right, using the neural network surrogate is a much more reasonable thing to do, because again, the sort of we know, right, if we don't solve the closure equation directly, we're going to be making some crime, right? All we're trying to do is not commit as big a crime as like replacing the whole thing by like a phenomenological model. I mean, we're not trying to build a plane, right, out of some composite materials that we all board and then hope that the simulations are enough to keep us in the air, right? We're just trying to accelerate some design cycle. Plus, it was nice to see how it would work. Oops.
So you are saying that because you have this non-linearity, I mean, in the closure equations that you needed, I mean, to use, I mean, that kind of tools to propagate uncertainty.
Right. So the deterministic homogenization, right, which is this business about getting the closure equation, is expensive, right? But the idea of having the whole point of the model, right, is to somehow incorporate this closure, because it's a systematic way of relating microscale, right, to the macro scale. And I mean, you have lots of these sorts of closures, right? I mean, you could also imagine, not here with this supercapacitor, but say you have a lithium-ion battery, right? Same sort of thing, right? You have a ton of phenomenological models that relate microscale to macroscale. But if you actually want to have your battery in the car, and you want to, maybe this is a good idea, we should think about this, battery in the car, and you want to sort of understand how it's degrading, then one needs to not look at the phenomenological models, right? You need to solve some complicated PDE problem, and it's not fast enough, right? You can't have it in the car. I mean, not helpful, right? You get the answer after the battery's already degraded. So that's a good question to have.
Okay.
You turned it off.
Thank you very much for your talks. It's very interesting. I have a question relating to your graph to represent domain knowledge. So yes. Saying if B is depending on A, then you make an arrow from A to B. What exactly mathematically happened in this arrow is like when we do some math with a neuron, or what happened inside it?
With the neurons. So here, yes. So what we have is a probabilistic graphical model, right? Which is, we say we have we have a joint distribution that we're interested in describing, right? So here, the joint distribution would be all the variables that are in the system, right? So the control variables, anything that was a bottleneck, and the output variables. And the graphical representation here of the circles and the arrows, it's just describing a conditional relationship between the two variables, right? So the one at the end of the arrow, right? This is a conditional probability, right? You need to know the first one, right? So when you write down the joint distribution of A and B, right? It's the probability of the density here for A and B, right? Is written as the product of the conditional density, right? A given B times the marginal density. Does that answer? And how one decides which direction it goes. Well, in the first model, right, that was chiefly by, for example, as I said, the engineers telling us that here are design constraints, here are things that we know about the system, right, that make us think that we're much more certain about this component versus some other component, right? So for example, the radius, this nice, the way that they make the materials is actually the opposite of sort of what you're probably thinking. They put down something and then they make some structure around it, and then they like wash things away, and it's complicated. And the putting down of the sort of little ball structures is less certain than the balls themselves, for example. And so in the model, the choice was made at the suggestion of engineers that the radii, right, were much more certain if we have these fixed cells that we're imagining to do this deterministic commoditization, right? You can't have everything be a free variable, right? I mean, something has to be dependent. Yeah, there's a geometrical constraint there. For some of the other things, the directions were decided by the physical model themselves, because you can't compute it without first computing something else.
I'm sorry, but I still not clear. So let's say you have you put a probability on A, yes, or you put a realization of A. So usually we use pin, for example, in neural network, then it should be realizations, if not a probability. So it's not so clear for me.
Right. So we're still training the neural network using realizations, right? But only realizations that respect the probabilistic graphical model.
Okay.
So you have a structured prior, not just independent, right? It's not flat in shape, right? The sampling is according to this structure.
Okay. So in the graph, you do not need to train anything.
Sorry?
In the graph, you do not need to train anything, but you
no. So there, that structure, as I said, that you keep like on the control variables, are things that you don't. That's the trouble, right? I mean, you keep it around, and then you're able to interrogate the model a little bit better at the end. Yeah. Sorry about that. I understand now what the issue is. The image with the graph. Yeah. No, you're sampling. Clear. You're sampling. It's fine. Realization.
We still have another question from Ben Mansour.
Can I turn on the light? It's getting dark, and I can't see people. There's like light coming at me. That's why I was down like this. What's the question? You're not doing it.
Yeah. I mean, you are doing upscaling, coming from the very atomistic level up to the
the microscale. So not atomistic there, but microscale.
Microscale.
Yeah.
So you pass like several levels of scale. So I'm just wondering, how did you do? How did you deal with the DFT? Because this is quite sensitive to the scale.
Right. So with the Langmuir model, right there, I was just showing the data there, right, that suggests that there's a linear relationship between changes in absorption energy, right, is computed using DFT. That didn't enter into the sort of like that wasn't part of the model there.
Oh,
Yeah,
okay.
that was the changes in absorption energies, right? How those two things are related. You can look at things that have been computed, right? We took it from a paper by some people at the University of Delaware, actually, in engineering, though not in math. And it's a funny thing to see, yeah, here they think that there's a linear relationship between changes in absorption energy of these two species. And in particular, if you keep that information, right, that you're not just sampling the changes in absorption energies independently, but you keep this conditional relationship between the variables, as you would expect, right, including extra information, means that you're actually reducing sort of the variance in the predictions that you're making of the coverage dynamics. So it's a nice example in that if you include this extra information, you get something for it.
I see.
Yeah.
Yeah, I see.
I see. Yeah. You have to run again, Nadir.
Okay. One more question.
So one more question, because you make a very nice comparison between Sobon's index and mutual information, but you also mentioned in your slide sampling methods, which is now very popular to explain the neural network.
Yeah.
Can you make also why?
yeah.
Can you also explain why you do not use sampling method?
The Shapley methods.
Sampling, yeah.
Yeah. I think, I mean, again, it was because the output quantities, right, were non-Gaussian, and that was something that also depends on a moment. And I think that, you're asking a question about matching moments or something like this, or some conditional expectation. I mean, I don't know if you have something that's non-Gaussian, yeah, how much trying to measure like the first moment or the second moment, or how the first moment and second moment of some inputs affect the outputs is going to tell you about a funny shape distribution. I mean, it'll tell you something. I just don't know what and how much it's telling you.
Yeah. Sampling method still compare the variant, right?
Yeah, exactly. Yeah. So
it's different than the Sobon method, that they do not make the independent assumption amongst the parameter, but it's still second model.
Yeah. And it's like, I mean, okay, we need something that's robust against the people who are using it, right? There's nothing telling an engineer not to use the Sobel index when they shouldn't. And then the poor PhD student who's designing the material has to spend another year in the lab, I guess. I don't know. So I think the obstacle to using like a distributional method, right, like the mutual information, which requires a lot of predicted data, right? You're trying to recreate a measure of discrepancy between distributions, right? So you need data to do that. That's overcome if you already have something that's going to spit out, data for you, a statistical surrogate. So you might as well use something that makes use of the fact that you have a statistical surrogate. Of course, maybe if you have like some scaling problems, like really big numbers of maybe you don't want to use the mutual information, maybe you use some other probability metric. There's many, right? And they have different properties. But that one is, I think, well known, mutual information. Its interpretation is a bit clearer. Yeah. You can use it to understand independence in the networks, right? Which is kind of what we were interested in. Yeah.
Thanks.
Yeah. Now we should clap before anyone else has a question. We're stuck here.
Yeah, if no more questions, let us thank again Eric. Thank you, Eric.